Hello, everybody, and welcome back to the channel. Sorry if I don't post that often, by the way. This is just kind of a side channel for me to document and have fun talking about data analytics. And I wanted to do that now. So I'm starting a new series about modeling that'll be good for anybody from just like an introductory level if you're either in high school or in a little bit of college. This will be very useful to you. Also, if you're outside of academia, this may be useful for business people as well to learn about how to study our world in a little bit more of a scientific sense. I think data is definitely on the rise with people taking data a little bit more seriously nowadays. And so I thought maybe now would be a good time to kind of document all in one place things that I know about modeling and how it may help you. So in this video, we're going to talk a little bit about introductory modeling steps, mostly with just the linear model and some of the basics that we'll carry out throughout this playlist. And yeah, some things I think that you will get from this are like how to handle scientific inquiry in terms of theory, enough math skills to address modeling problems intrinsically, and then also uh, knowledge on how this can help you or your business, examples or future readings, code. This is mostly going to be around the R language, but it can be easily transcribed into even Excel, I think, for especially this video. If you are new to R, by the way, click the little thing up above, the little card that just popped down. Click that. That'll teach you how to install R and some of the settings that I'll be using. But yeah, so also I'm hoping that the series provides some entertainment. So hey, there's that. So yeah, this will be good for basically anybody in a little bit of high school, all the way through a bit of college. It'll definitely draw from some things that we learned in high school, and then kind of apply them to our jobs today. And yeah, so there's that. If you're just kind of even thinking about if modeling is really for you, or if you are in a position where you have been asked to do modeling, and I'm sorry you're here, but stay with me. We can get through this. You may want to check out another video I released a couple weeks ago about like theory and modeling building, and if modeling is really for you just yet. That video digs deep into like causal questions versus correlational questions about modeling and some of the steps that you'll have to take in order to really get your data in like a good place for modeling. So if you're here for like a more practical sense, that video might be good for you as well. I would click this card up above and visit that. Also, both of these videos will be linked in the description. So let's get started. I'm sorry for a little bit of a longer introduction. You know, the first video of any playlist, I think it's going to be like that. But here we are. You jumped ahead, and now we are talking about linear models. So let's think back. Let's put on our little thinking caps and go back to whatever year you were in high school. And go back, and you may remember an equation that was mentioned, and at the time you were taking notes about it and you said, I am never going to use this in all of my life. Well, here you are and you're about to use it. It is y equals mx plus b. Yeah, that was important. I went full black screen for that one, didn't I? So y in this equation, so this is the equation for a line, by the way. And y in this equation is our dependent variable. Well, our dependent variable is the thing that we really care about. It's the thing that we're trying to predict. Maybe it's sales, maybe it's customer satisfaction, maybe it's the fertilization rates of a particular type of corn. It really could be anything. It's a success of a political strategy. It could be, you know, levels of attraction. I mean, anything that we're curious about in life, why that variable y is going to be the thing that we really care about, and it stands alone on the left hand side of the equation. So then let's talk about the right hand side, right? Sing along with me if you remember the full equation. Y equals mx plus b. So x here is our independent variable, and those are all of our predictors of y. So we could have multiple of these, but basically x is just a data set. Like think of Excel, where you have a column of data, and in there is a number or maybe Well, it has to be a number, yeah. So it's a number, but that number could represent, categories. It could represent, anything that we want to numerically represent. And so we have a bunch of these x variables, and then we also have that one y variable that we really care about. So then what are m and b? So m was our slope, if we remember that. And our slope is basically just the line. It's the pitch of the line that we've drawn. And then b is our y-intercept. And b is kind of interesting. We'll talk about that here in a little bit. But for now, let's just cover what we've learned so far. So we have y equals mx plus b as our beginning linear model theory. And if we plug the data into this equation, we would get basically just a one variable line chopping through our data. And then what we could do is look at that line and say, you know what? If we had a theoretical another point that was an x that came up in our data, like let's say that we had, I don't know, age, and we were predicting how much soup they would buy. I just bought groceries online, so this is on my mind. Sorry. So we're considering the age of the person and how much soup they would buy. And we have a really, let's say we work for Kroger or some big grocery chain, and we have a lot of data. Let's say we plug in like 10,000 cases of somebody buying soup, and we know their age. One, that's kind of creepy. I hope they don't know my age, but let's say we have that. And then we go through, and let's say we don't have any data for people that are 81, but we have data all around that, and we have a line chopping through that graph that'll tell us the likelihood of somebody buying soup just based on their age, right? The relationship between these two variables, the y-axis and the x-axis. And so what we could do is theoretically follow that line, look at the x-axis and say, well, you know what? We don't have any data that are people that are like 71. Let's say, I forgot the number I said earlier, 71. But if we just go to the x-axis and go up to that and hit the line, that's likely where we're about to be. Yeah, so that's kind of where we're at right now. But we can take this simple linear line regression and add a lot of math and science to it, and kind of talk about it in a little bit more of like a statistical way. So we're going to do a little bit of that in this video. I hope I don't lose you. I'm going to try to keep things pretty high level just for the first video. The worst thing I could do right now is to talk over everybody's head, and then they don't click on any of the other videos, right? So let's try to keep things pretty simple for the first one. And honestly, I think a lot of these videos are going to be pretty simple as well. So foreseeably right now we have y equals mx1. We could also have mx2, mx3, all the way down the line plus b. And, in Excel maybe, or in a data table, this would just be one column of your y's, x1, x2, x3, and then the m is the slope for these predictors. Let's use a little bit of a different math notation, by the way. Let's use a notation taken by, I think it's the Econometrics Notation, where we still have the y, but we'll call it beta 1 or beta naught is our x1 predictor. And then also for every beta I, so subscript I is just going to be the number that we have here. There's no real math going on there. That's just an indicator. It's just describing. It's like a name tag on all these little different variables. So we have beta naught as the sort of lead indicator here, and then beta 1 through beta n, and then you also have x1 through xn. And instead of b, let's call it e for error. Why not? And so we do this, and you may be wondering, well, like, what was the big deal with the y-intercept and changing to e? Well, e is basically accounting for bias in our model. So that's going to be the leftover stuff. And if you think of this model as like a description of the universe, then we're thinking about cans of soup, by the way. And let's say we put in age. Let's put in somebody's like liking of soup. Like let's say we survey them, and we have if whether or not people like soup. Maybe we have if people grew up liking soup, and a bunch of other stuff. But we didn't get everything, and it's almost impossible to get everything. I'm not going to get into like frequentist and Bayesian debates here, but I'm just going to say that it would be almost impossible to measure absolutely everything for why somebody bought soup. There's probably a lot of biological decisions going on there. Maybe they liked the color of the can that they saw. Maybe it was at eye level. And yeah, we can measure some of these things through like psychological studies, but I'm skeptical that we'd be able to measure everything. And so we add an error term at the end. And then now this is a model where we can plug in everything and then everything kind of left over where the line doesn't perfectly match every point like a connected dots graph. That's our error term. And we'll talk a little bit more about that in the future. And I don't want to get too much into how the transformation of the y-intercept goes into an error term. I found a really, really good blog that goes through it. I'll link that down in the description below if you guys want to check that out. That blog was very, very good in talking about that sort of transformation. But now we'll just take it as truth that our y-intercept turns into our error term. And the goal of this model, by the way, is just to shrink the amount of error that we get in the model. So imagine if we have a line plot, and maybe I'll pull one up here to the side. Imagine we have a line plot like this, and the line is cutting through all of these data points, right? Just like we had before. And imagine that there's these little squares that connect the line estimator from the actual point. And so we get these little square boxes, right? The distance between the line and the actual data point. And so whereas like the distance between those could be called a Euclidean distance, we're not talking about that in this sense. This is actually just a square, right? And so what we want to do with our estimator, ideally, is have the least squares possible. We want to have very, very tiny squares as we cut through this. And so this is what OLS regression stands for. If you've ever heard OLS, it's called ordinary least squares. And this regression type has also been called BLUE, B-L-U-E, which is an acronym for Best Linear Unbiased Estimator. And so way back in the day when this was being talked about, people were ranting and raving over OLS regressions, and still today they are used, as the cornerstone for a lot of why the planes fly the way they do, or Facebook targets ads towards you the way they do. Linear regressions are still used everywhere because they are so blue. And let's unpack a little bit what blue kind of means. Best linear unbiased estimator. Those all sound like great words that might fit really nice on a resume, but let's actually get into the interview here, I guess, and talk a little bit about what that means. So linear just means that it's a certain class of estimators. Unbiased means that in sampling, if you just keep sampling more of a population in that X term, for example, let's unpack that a little bit. So let's say that we are interested in this soup example. I can't think of a new one right now. So we are interested in soup. And let's say we do take a sample of all the Kroger participants. But let's say we only have data on people that use a Kroger card, right? I think that's kind of how that actually works, is that Kroger gives you discounts in order to take a bunch of your data. But so let's say we only have that sample. Well, in a full universe of everybody that has ever purchased soup, we only have, concentric circle less than that total population. And let's say that in our model, we weren't able to run everybody, or we only did a sampling of like 2,000 people. Well, then we only have 2,000 out of that total universe. But the OLS regression is blue because if we were to keep taking more and more samples out, let's say it's even random samples, and just like the bag of marbles statistical question that we all shudder over when we hear about, if we were to just keep taking new samples out, it would eventually reach, if we accumulate all of these samples, to be just this unbiased estimator that is more or less the truth of the whole thing we got going on here. So we'll eventually reach the true population size, right, of everybody that's eaten soup or everybody that has a Kroger card. I don't know if there's like a theoretical difference between those two people, but if we were to just keep taking samples out of the population, we'd have this unbiased result. And so it is unbiased in that way. Also, it's unbiased in the fact that it minimizes variance, so it behaves really well with large samples. Our function earlier, or our equation earlier, does. So it's an asymptotic property that works really well with larger sample sizes. And so as we increase that sample size, the bias tends to go away. That's what the asymptotic property is. Are you taking notes? This is going to be on the quiz, by the way. So, um, so yeah. So for all of those reasons, this is the best linear unbiased estimator. Another reason is that as the variance converges to zero in this equation, our sample sizes increase, and so it's very consistent. Yeah. And I'll include a blog down below if all of that was a little bit jumbled up. There will be a blog down below where you can read more about the blue properties of the Ols regression. So what are we left with after we model this, right? So let's say, yeah, okay, this is all great. I'm interested in modeling. Let's hop in and let's do this. And maybe you even do a quick Google search on how to do it, and you've already ran a model. And now you're wondering, like, well, how do I even interpret what we kind of got here? Well, one way to do that would be to assess the R squared of your model. Now, the social scientist in me is saying, let's pump the brakes a little bit. Let's talk about what the model is really telling us. Let's think about the sample sizes and like really think through what exactly we did. But let's ignore all of that for this introductory video and just talk about R squared. So if you run this model, and say you include 3 different variables on your soup prediction or whatever, and at the end, in the model results spit out to you an R squared. And maybe it's an R squared of like 7 or something. It would be like 0.74. Let's say that. But what is this really telling us? Well, the R squared is basically a calculation of the RSS over the TSS, which is the residual sum of squares left over from our analysis over the total observed squares. And so this is kind of loosely understood as the amount of variance understood in our model. And so check out this picture over here, over here, this picture right here. So in this picture, we have on the left a residual sum of squares left over are pretty small, right? Those tiny little boxes I was talking about, those are a little bit smaller. So in the left, the tight packaged line would have a really high R squared value. And in the right, it would have a very low R squared because that line isn't really explaining exactly what all of those are. I think it's doing a good job, but it's not nearly as tightly packaged or explaining all the variance that it is in the left image. So that's kind of what R squared is going to tell you in this. And sometimes it's hard to graph that and show that visually because let's say you have like 14 models in your variable, or you have 14 variables in your model, and you're going into a business meeting and you want to explain how something's working, how you're selling soup. And so you have this and you can't really graph a 14 dimensional graph. I mean, you can describe it, you can describe anything in 14 dimensions, but like you can't really graph that and show that. You could show it in like 3 dimensions. You may be able to kind of show it with like color and other things, but not really for that many variables. So that's why an R squared is a useful descriptor of how well our model is doing. I will say that in social sciences, broadly speaking, you're going to have a lower R squared just because it's the social world and there's a lot of things going on. Somebody maybe have stubbed their toe that morning and that's why they're a little bit more angry, and then that spirals off into a bunch of other things. So there is a lot of things that bake into the social sciences. So just keep that in mind. But overall, it is still a science, and at the end of the day, you are still predicting things. And if you don't believe me, then politicians do it all the time with the ads they send to you. So yeah, so that covered that covered quite a bit, I think, of stuff for this one like introductory episode. I think future modeling videos will have a lot of the same sort of language in it going forward, and maybe I'll show like even more code and stuff. I'd be really interested on your feedback if you want to leave that below. I thought it was helpful to just kind of put this down into a video for somebody out to help somebody out. But this video is getting to be about 20 minutes long, and I think that's a bit long for an introductory video. I hope this has helped somebody. Let me know down below if you have any feedback, concerns, or insights. I'm happy to expand more on this and talk about the different modeling types, maybe some examples, maybe talk about a research paper or two that use some of these examples. And yeah, just happy to review a lot of this modeling knowledge with you all. So take care, everybody. It was good seeing you again. And